Hello. In our last class, we have discussed that simple ring. Okay, that a ring which has only ideal is your that trivial one, and that ring itself. That is, it has no non-trivial proper ideal. Okay, so and we have some theorem. Okay, now we are move to next portion, that is your principal ideal. Before that, we'll discuss the already it is discussed in the class. Just see what are the subring and ideal of Z. Okay, so you have to find basically. Okay, so how you will find this type of thing? You know that whatever it is subring or ideal, that must be a subset of Z, right? And you know mz is always a subset of Z, like 2z 3z, that type of thing. And if you apply all the property of your subring, you will see that will be obviously satisfied. And after that, already in the ideal chapter we have checked that mz plus dot, this is a subring and it satisfy that your ideal property also, basically r into a or a into r, this type of element also belongs to your mz. So in this way you can prove that mz plus at the subring or ideal will be this. Okay, so even without this mz plus dot, there are no other subring. Basically all the subring or all the ideal of Z must be of this form, this type of quantity. Okay, this is already discussed earlier, I just recalling. Okay, there are similar type of thing. What are the subring and ideal of Zn? Okay, so how to check this type of thing? Subring of Zn. Okay, so how to find this type of thing? Basically, suppose you have some n, then for this n you have to find a divisor. Okay, for example, suppose you have z6. Okay, so what are the divisor of 6? For this one you have to consider 1, 2, 3 and 6, right? Now whatever the divisor, just divide with that number and then make that a generator, right? For example, how to find the first, you have to find subgroup type of property, right? What are the subgroup of your z6? So basically if you consider this divisor 1, so 6 by 1 is 6, so generated by 6, that will be generated by 6 means 0, right? So just singleton 0, this is corresponding to 1. So for this two number, so if you divide 6 by 2, that is 3, right? So you have to make that generated by 3. So what are the element will be there? So 3 bar, and then you have 6 bar, that means 0 bar. So basically 0 bar and 3 bar, right? These are the for this number 3, so you have to consider 6 by 3, that is 2, right? So in this way, what is this group? Basically it looks like 2, 4 and then 6 means 0. I am writing fast this way. Okay, and obviously generated by this, for this divisor 6, so what is 6 by 6 is 1, so generated by 1 is itself z6, right? So these are the possible subring of your z6. And if you consider the ideal property, you will see all the thing will satisfy the ideal property. Okay, next I am going to discuss the principal ideal in a ring. let S be a non-empty set. Okay, suppose this is your R. Okay, and inside that R, suppose this is your set S. Okay, now you will say, basically the question is asked for ideal generated by S. So how to find? Basically you have to find all the ideal that contain S. Maybe you have a one ideal like this is your suppose I1. Okay, suppose another ideal that is your I2. So in this way you have many ideal that contains S. Now you have to find the intersection of all the ideal. That will say the ideal generated by S. Okay, so the definition is the intersection of all ideal of R subset S is an R smallest R meaning the subset S. Okay, so S you have something, then the intersection of all ideals of R that contains S is also, already you have seen the intersection of ideal is itself an ideal. This proof we have done in our last class. So that will be also ideal. That ideal it is, and if you take that one, that will be the smallest ideal of R containing the subset S. Okay, this ideal is called generated by S set. Now instead of this S, if you consider a singleton element, obviously you can consider just S equal to singleton A. Okay, then that ideal will be generated by that element, right? That element is actually called the principal ideal. Okay, so you can think you have a ring R and this is a singleton element A, and suppose this is your I1, this is your I2, this is your I3, maybe like that. Okay, then intersection of all the ideal you have to take. You will see that ideal will be intersection, maybe for this one example maybe like this, right? This one, this ideal itself a ideal, and that ideal you will say the principal ideal. Okay, so now I am writing the definition of principal ideal. Okay, so this is just ideal generated by a set S. Okay, so maybe we can write that ideal generated by S by a set. Okay, this is the definition. Next we are writing the definition of principal ideal. Let R be a ring and A belongs to R. The smallest ideal of R containing the element A is said to be a principal ideal of R. Or we can say that ideal generated by A also. And it is denoted by this type of thing. Okay, so now if you consider the ring, suppose Z. Okay, now in that ring, suppose you are considering 2 is an element. Okay, now if I consider what will be the ideal generated by 2, so obviously if you consider this thing, so you have to consider all the ideal that contains 2. Okay, I think if you try to construct that 2 element, so there is only one option, right? So it is, if this is Z, if you this is 2. Okay, so 2 contain the ideal only your Z itself or your 2Z, right? So if you consider Z and you are doing with 2Z, so obviously you will get 2Z, right? So the ideal generated by 2, it will be like 2Z. Okay, so if you consider now suppose 4 or maybe 6. Okay, so here you will see this 6 element, obviously 6 element in belongs to 2Z also, right? 6 belongs to 3Z also, 6 belongs to 4Z also, 6Z also. So if you do the all the intersection of 2Z, 3Z and 6Z, obviously you will get 6Z. Basically if you are trying to find for the number M, you will get MZ. Okay, so this is a result that in a ring Z, the subring MZ is a principal ideal. You can say generated by M, right? This is your one result. Okay, suppose this is example 1. Suppose you are considering Z cross Z. Okay, and this ring, and in this ring suppose you are considering the element 1, 0. Okay, so if you are trying to find the ideal that contains this 1, 0, so you will get basically Z cross 0. Okay, So Z cross 0 will be the ideal that generated by your Z cross Z. You can read this example in the schema of a book. Okay, yeah. So after that we have a result. Let R be a commutative ring. With unity you have, and A belongs to R is some element. Okay, then the set RA. What do you mean by RA? RA means RA where R belongs to R. Okay, is a principal. Sorry, this is principal. Okay, yeah, principal. I think. Of R generated by A. Okay, so this is a theorem. The proof is also simple. You can do this homework very easy. Okay, basically array, this type of element will be a ideal that you have to prove, and then if you consider any ideal that contain your I A element, okay, then you will show that array will be subset of that ideal. Okay, so in this way you can prove that thing. Okay, so this is your homework. You write this theorem, and if any issue, then you send me in the WhatsApp chat. Okay, then we'll discuss in the next class. Okay. Okay, so next you have a definition that is which is called principal ideal ring. A ring is said to be a principal ideal ring if every ideal of the ring is a principal ideal. Okay, so every ideal will be principal. That is, if you consider any ideal, that will be generated by singleton, some singleton element. Okay, so then you will say the whole ring is your principal ideal. What is the example? Easiest example is your Z. Why? If you consider any ideal of that, for example, if you consider 2Z, that will be generated by 2. If you consider 3Z, that will be generated by 3. In general, MZ, you know that every ideal of Z will be of the form MZ, right? And that will be generated by M. So you can say that's why that Z is a principal ideal ring. Okay. Similarly, Zn, if you consider. So in the Zn, I told you what are the subring and what are the ideal at the beginning of the class, right? And obviously that will be generated by some element, right? For example, this in where we have, yeah, in this Z6, if you see, there are actually 4 ideal, okay, and every element you will see there is generator. For example, if you say this ideal, so what are the generator? You can say 2 bar, right? So in this way we can say Z8 is also a principal ideal ring, okay. Okay, okay, suppose maybe these 2 are the main example, okay. Next is your prime ideal. You know prime number, right? Like prime number means that it does not have any divisor, right? So there is a relation with that prime number, so that's why it is called prime number. Let's see what is the definition. So this is very very important. When the online class start, we will discuss regularly, okay, and ask everyone this prime ideal, very very important, okay. So in a ring R, an ideal P not equal to R is said to be prime ideal if for A comma B belongs to R, AB belongs to P, imply A belongs to P or B belongs to P, okay. This is the thing. So in a ring R you have a ideal P. Now if you see that AB is a number which belongs to that number P, then either A or B, obviously in your P. For example, if you consider Z6, okay, so in that Z6 ring, you know how the Z6 Z6, instead of Z6, suppose you are considering 6Z. 6Z is a ideal of your Z, right? Now you see 2 into 3 equal to 6, that element belongs to 6Z, right? But obviously this 2 and 3 both belongs to Z, right? So this is satisfying, and you are saying this thing belongs to this. So is it imply 2 belongs to 6Z or 3 belongs to 6Z? Obviously no, right? So you can say 6Z is not a prime ideal, right? Example 1, so you can say 6Z not prime ideal of Z. Now instead of that, if you consider 2Z, okay, so in this 2Z, this is a ring of this one. So if you consider any element A and B belongs to Z, and suppose A dot B belongs to 2Z, so if your AB belongs to 2Z, so obviously AB will be of the form some 2M, right? For some M, you can say, okay. So whatever whenever your AB equal to 2M, so obviously 2 divides your AB. So whenever this type of thing happening, either 2 divides A or 2 divides B. So accordingly that you have A belongs to 2z or B belongs to 2z, right? So from there you can say your 2z is a prime. Okay, so in this way you can able to prove. Okay, next. So in the end basically you will see later that pz, whenever you have this thing, this pz will be a prime ideal. Okay, oh, this is the next theorem actually. Okay, theorem. So the prime ideals in the ring Z are the ideals Pz, where P is either 0 or A prime. So basically whenever your P is 0, then that is your just singleton 0, that is the trivial ideal or null ideal. Okay, so we are not interested in that one, but anyway, whenever your P is prime, so basically then actually your Pz will be your prime ideal. Okay, so the null ideal 0 in the ring Z is a prime ideal. Why it is prime? If you have AB belongs to your that 0, so obviously then either A will be 0 or B will be 0. If your AB belongs to singleton 0, then basically AB equal to 0 imply AB equal to 0 imply equal to 0. Or B belongs. Okay, now consider let AB belongs to PZ. Okay, some AB belongs to Z. Then AB equal to some P into M for some integer M. Therefore you can say P is a divisor of AB, right? So this imply basically if your P divides AB, so obviously P divides A or P divides B, right? That means you can say A belongs to PZ or B belongs to PZ, right? So this proves that PZ is a prime ideal. Okay, now conversely, suppose What is the converse part? Basically that every prime ideal of the Z is actually in that P Z form. Okay, so you will consider some P ideal, okay, that obviously in PZ form. Basically, you know, every ideal of Z will be some MZ form, right? Now you have to consider that M must be prime whenever it is prime ideal. Okay, so conversely, so এখানে ওয়ানলি ওয়ার্ডটা only what we लिख सकते हैं theorem. Okay, then it will be more focused on the conversely part, otherwise you may continue up to this. Yeah, so let P which are not 0, so you have considered that Pz P equal to 0 and prime that are the prime ideal. Now basically you have to consider if it is some composite number. For this one, that will not be a prime. Okay, let P equal to U be a prime ideal in Z. Since this is already a result, every ideal in the ring is a principal ideal, so you can say P equal to P into Z. Integer P. Okay, so obviously P not equal to Z as P not equal to 1. Okay, so we are considering that one case, because if it is 1, so then it will be Z itself, right? And you know P cannot be Z because whenever you are writing the definition of your prime ideal, that will not consider the whole ring, right? P not equal to 1. Okay, so we are not considering this thing. So already we have proved that P equal to prime, that is prime. So now consider, let P be a composite number. So let P equal to U into V for some integer U and V. Since your P is a prime ideal, so obviously UV belongs to P. This imply U belongs to P or V belongs to P. So this means U belongs to P into Z or V belongs to P into Z. So u belongs to pz, that means what's happened, basically p divides u, right? This imply p divides u or p divides p. Is it possible? You have this type of relation. U is a number between 1 and p, v is a number between 1 and p, and you are getting p divides a and p divides v. So p is a prime. Okay. Okay. Next you have maximal ideal. So let R be a ring and ideal m not equal to R, same thing, this condition is in our prime also, is said to be maximal ideal if every ideal u of R satisfying m subset of u subset of R, then either u equal to m or u equal to R. So what is this time? Maximal. Okay, that means you know that there is some chain, I think you have done in the lattice courses or earlier. Okay, so that one will be the maximum thing. For example, if I say 12z, you know 12z will be inside your 4z, right? 4z will be inside your 2z, right? And 2z will be inside of a z, like some chain. So obviously that will cannot be z, so you can say this 2z is the maximal. Okay, because in this 2z and z there cannot be any other ideal. So here you see this is your, you can say m. So it is saying if you have some, this is your R, if you have some u inside this 2, so then either u should be your m or u should be your R. That means in other words you can say there cannot be any other u in between your that m and R. So then you can say m will be the maximal. Okay, this is the definition. Okay, so this is the example, so we can write example 1. So you can say 2z is a maximal, ideal. So basically if you try to consider any u that contain 2z, so you will get that u will be either the whole ring z or your 2z. Okay, so you just have a reading in the SKM of a book that are very easier. Okay, and your home tasks, homework 1, you send me this. I am sending two things. Suppose let C AB be set of a real valued continuous function. I am giving two set. Suppose you have a S1 which says that A belongs to C A B, such that f of A plus B by 2 equal to 0. Okay, and I am giving you two set. A belongs to C A B, such that f of A plus B by equal to 0 and f of three. Check the maximality condition for S1 and S2. Okay, so this homework is very important. Everyone you have to do. This is, you can say, your just this is one page you have to do. This is your assignment 2 also. You send me by maybe this weekend. Okay, nine, 10, 11, 12 April. Okay, so yeah, after that we'll continue. Stop the class here. Okay, bye.